Ya vas a ser conocido por el todo YPBB. Cachalera. Ya lo mezcló otra palabra. Quinchadera. Obvio.
Okay, so we'll carry on where we left off.
Sueñe. Tu sueñe. Eso. No te comes.
Okay, so at any rate, to sum that up, at the high stand of sea level, your shoreline is going to be a landward of where it would be during a low stand of sea level. So your shoreline here at high stand is there. That's when these major deltas form, where you have rivers, large rivers coming in. And then, and that would be at this point on the sea level curve. And then at low stand of sea level, your shoreline is going to be out here. Continental shelf is exposed. You create these incised valleys, and then they backfill them on the next rise in sea level. And the result, as you go from one cycle from one end to the other, is a depositional sequence bounded by unconformities, usually, or what we would call, in sequence stratigraphy terms, we call those sequence boundaries, SB. Okay, so when I showed this picture yesterday too. When you look at a shoreline like this, or a shore zone, you've got these different depositional environments there. You've got a beach right there. You've got sand dunes usually behind the beach. And the reason you have that is because winds usually blow on shore, and so they pick up sand from the beach and pile it back behind the beach as sand dunes. And then you've got muddy lagoonal deposits behind there. But the picture you're looking at represents just one instant in geological time. And with time, you're going to get movement of the shoreline, as I've said many times here before. At any one instant in time, you're going to, in many shorelines, not all shorelines, but many shorelines, it's a very high energy zone here, where you have on your beach, where you have waves coming in and out, or the surf coming in and out. You create these waves and you get a high energy zone. So if you look at this little cross section here, what you'll see is a high energy zone here where the waves break, and the further seaward you get, the lower the energy of the depositional environment, the less current action that you have on the seafloor. And it's only when you get up into the real shallow that your waves start to feel the bottom, and they roll over and to form the surf. So that's a high energy zone. So if you imagine now, over an interval, that's a high energy zone at an instant in geologic time. If you think in terms of geologic time over a certain time interval, then we have marine transgression. all of these environments are going to move landward because they're all related to where the shoreline is. So all these environments are going to move landward, and they'll be deposited on top of the preceding deposits. So during transgression, you might find a lagoonal deposit overlain by a sand dune, and then overlain by a beach deposit. Now, when you go in the offshore here, there's also different sedimentary environments because your wave energy is getting less as you go further offshore. So we have names for that too. We call the very shallow offshore the upper shore face, and then the middle offshore, we call that the middle shore face. And if we went further and further seaward on the continental shelf, we'd have what's called the lower shore face. So, and each one of those gets finer and finer grained as you move into progressively deeper water away from the shoreline. So your upper shore face tends to be very sandy, nice high energy. Your middle shore face starts to have some mud in it, and your lower shore face tends to be very muddy and have more mud than sand. And then if you went even further out on the shelf, you'd lose all your sand, and you just have a muddy seafloor. So that's kind of the configuration, but the important point is then that during transgression, say you're standing right here during a marine transgression, you're standing right there. The first thing deposited at your feet will be the lagoonal deposits, and then you're going to then get your dune deposits overlying that, and then your beach deposits overlying that, and then your upper shore face, middle shore face, and lower shore face. And you can recognize these on well logs, as I'll point out in a couple minutes to you. Well, the opposite occurs during regression. During regression, the shoreline, or progradation, the shoreline recedes, goes seaward, so you tend to get more erosion. And so as you drop sea level, any rivers in this area, like these kind of slow-moving rivers here, they're going to become higher energy, flow faster, trying to get to that shoreline as it moves seaward, and so that's when you get your erosion and the carving out of your incised valleys. So what you have up on in this area then is more of an erosion surface, and that's when you get your erosion surface or unconformity, or as we call it, sequence boundary. So, picture represents an instant in time, but we're thinking in intervals of time, not instants in time, but intervals of time where sea level either rises and the shoreline moves landward, or sea level retreats and the shoreline moves seaward. So here's just a little cartoon, or a series of cartoons, that illustrate what happens. So up here we have a delta that's been carved into by an incised valley. So the orange there is the incised valley. Our shelf edge is right about in here. And so this is the sea surface, and here is the sea floor. Okay. That would be the case, say, in this part of our sea level curve. Okay, this part of our sea level curve where we're eroding. Dropping sea level, the shoreline moves seaward, and so we get erosion. So, falling sea level, shoreline moves seaward, the shelf becomes exposed and eroded, and so you get an erosion surface here, which we call a sequence boundary. Now, let's go turn around and rise sea level to this position here. And sea level is now, the shoreline is now way off the picture here. And so you're getting deeper water at any one spot along this profile. So if you were standing right here, what would be deposited at your feet during a falling stage of sea level would be the sediment that was eroded out from that the formation of the incised valley, and that sediment ends up down as a submarine fan down here. So during the falling stage, once again, you get in deep water, you get submarine fans. In shallow water, the same geological time interval is represented by an unconformity surface, okay, or a sequence boundary. So you've got a sequence boundary forming here, and a submarine fan forming down here, with some feeder channels down around here. Now during the rise in sea level then, if you're still standing at this one spot, sea level rising, meaning you're going to get finer grained sediments deposited on top of the submarine fan. And what I show here is just kind of a blanket-like mud. That's going to be your condensed section, by the way, or where your unconventional resource shales are deposited at that time. Sea level rising, finer grained sediments being deposited, and organic matter, which also tends to be lightweight. Organisms that live in the water column, plant material, things like that will tend to be more prevalent, form in this environment. So we have a rise in sea level now. We're coming around our sea level curve, and the shoreline moves landward, and we get our organic rich condensed section forming, and that's what this blanket shale is, blanket mudstone. And one thing I do want to point out is that, and this is the exception, when you asked me the other day, you were asking about the exception. I said there's one more exception to that rule about sequence boundaries and all. And this is the exception. In shallow water, in the shallow marine environment, go back to that picture. In that shallow marine environment, during a very early transgression, when you get a sea level turnaround and starts to transgress, because this is a high energy zone, as it moves up across here, it's going to erode these sediments. As that shoreline moves landward, it's going to erode the sediments. We call that a transgressive surface of erosion. And to answer your question of the other day, here's the transgressive surface of erosion. It'll be sitting right on top of your sequence boundary. So you get a combination quite often, only in shallow water, you'll get a combination of a sequence boundary that forms an erosion surface during the drop in sea level, and then during that very early rise in sea level, that surf zone will come across and do some more erosion, and that's called the transgressive surface of erosion. It's not a T, it's an E. Okay, so that's the exception. When you mentioned the other day that that you call these boundaries sometimes, and that would be a case where you'd have a combined sequence boundary and transgressive surface of erosion. It really represents a long interval of time where you drop sea level and then early rise in sea level. But so you could call that a boundary, or I call it a combined sequence boundary transgressive surface of erosion. And you don't get those in deep water. They're a product of shallow marine or non-marine sort of environments of deposition. Okay, now there's one other complication, and up to this point in what I've been talking about, I've been saying that during high stand of sea level, your shoreline is moving landward. And that's not really the case. I kind of lied to you a little bit. Okay, now I'm going to tell you the truth. See, we're going to get to the truth. And what happens is, and this is very confusing. The word high stand of sea level is a word that the Exxon folks came up with, and it really is not a very good word. People are going back to more the idea of regression or progradation rather than high stand of sea level. Because what's happening is sea level still is rising, okay, and that's up in this part of our sea level curve. Sea level is still rising, but the rate of rise of sea level is diminishing. That's why the curve is starting to flatten out up there. And so what happens if you've got a constant supply of sediment, during that period of time, you're going to the difference between the sea surface and the sea floor is going to be filled up with sediment because the rate of rise of sea level is less than it was during this transgression. So you really have, when you look at this curve, you really have to look at the slope of the curve and how the slope changes with time. So here, a steep slope. Time is your horizontal axis. High stand to low stand is your vertical axis. So a steep slope here means a relatively rapid fall in sea level. A steep slope up here, a rapid rise in sea level. And in that case, with a rapid rise in sea level, you've always got space between the sea surface and the sea floor. And even though you're depositing sediment, because sea level is rising rapidly, the shoreline will still move landward. But then when that sea level rise starts, the rate of rise starts to diminish, that's when you get less and less space between the sea surface and the sea floor, and so you prograde sediment out there. That you prograde it out, and it causes, what happens? It causes the shoreline to be pushed in the seaward direction. Okay, so sea level is still rising during high stand time, but the rate of rise is less. The rate of rise is less, and so during high stand time, you get your progradational deposits, which the most common one is your deltas. Okay, so you get your deltas forming during high stand time. For the most part, there is that exception I talked about yesterday. And during low stand time, you get your submarine fans out here. Okay, so here's the delta. And the submarine fan is older. Okay, your horizontal axis is time again. So the formation of the submarine fan occurs first. And then later on, you get during the rise, that's when you get your transgressive deposits and your high stand deposits. Okay, so they occur there. So they're younger through a sea level cycle. They're deposited after the sea level has fallen.
I have a question.
Yeah.
So here we are looking at what happens at the last part, at the end of the sea level rising.
Yeah.
And we can see there is a difference in the behavior.
Right.
What about at the beginning of the sea level falling?
Is that a high stand too?
No, it's starting, well, you can see in the curve, it's starting to drop. The rate of fall is first slow, and then it normally picks up. So the rate of fall, by the time you get down to here, the rate of fall is pretty fast. Okay? And then you get a turnaround. What happens during the turnaround is the sea level doesn't move much at all. Okay, it moves a little bit, but then you come up the curve like that, and then the rise in sea level is rapid, up to the point where it starts to decrease in the rate of rise. Okay.
So at the very beginning of the fall, when it's low, still fluvial, we can assume it's still gonna form the marine fan, or what can we assume?
Well, actually, it's a little more complicated because there's one phase, this very early phase of fall. What happens is that your sediment up here, if you're dropping sea level, what's gonna happen to the pore pressure in the sediments? Pore pressure is gonna go down. So you create an instability in the sediments. And so the first type of deposit that really forms is not as shown in this simplified diagram, but it's one of these, what we call a debris flow or a mass transport, where big blocks of mud coming from the upper slope will come down and be deposited in the basin. And I think I show that later on. So in reality, this is a simplified diagram, but in reality, you have this debris flow type deposit, big blocks of the upper slope that have rolled down because you created that instability when you drop sea level. So that's the first thing that is deposited, and then you get into that rapid fall in sea level, and that's when your submarine fans are deposited. Very predictable, you know, if you're out, I guess you guys don't do any exploration for deep water deposits, but it's pretty easy to see them, the deep water deposits on seismic, because what you look for on a seismic section, on a vertical seismic section, you really look for a seismically transparent zone. In other words, no internal reflectors. And that's usually what these debris flow deposits look like. They're all kind of jumbled up because they've been rolling down the slope, and so you don't have any continuous reflectors, so you get a seismically transparent zone. And then above that, because your submarine fan deposits are layered, they deposit in layer fashion, so on the seismic line you just look for a seismically transparent zone and overlain by a bunch of continuous high amplitude reflectors. That's how you explore for deep water sands. That's how you should explore, or the primary phase of exploration. And when you look at it that way, you can often pick those out. It's all pattern recognition. All of this is just, in fact, that's why computers now, there's several computer programs now that, you know, you put your input data and you punch the button and out comes your stratigraphic interpretation, because this is all predictable. And this is the stratigraphy that develops both at one spot over an interval of time and across over an interval of time. So there's a couple of, I don't use them myself. I prefer to use my brain power a little bit more. But there are programs you can buy, you know, that will do all this stuff for you. So, and interpret your seismic record and tell you what type of deposit you have by the characteristics. And because they're predictable, the sort of stacking you get. Okay, so going back to my little lie that I gave you, that during the high stand of sea level, the shoreline does not continue to move landward, but again, with the deposition during a time of a relative slow rise in sea level, shown by the flattening of the curve, you're going to deposit these delta deposits. They're going to prograde and they're going to push the shoreline out. So if we go back to the beginning here, the falling stage, here was the shoreline. During the rising stage, first you have your transgression, and that's going to put the shoreline back there. And then your high stand deposits, this is where your shoreline is going to be. Okay? So the little lie that I told you, more of a fib, not a lie. Not a bold-faced lie. I would never do that to anybody. But when I said earlier that during high stand you're still moving landward, the correct way to say that is your sea level is still rising, but at a slower rate, and so the sediment that's deposited pushes the shoreline seaward. Okay, so that's the correct statement. In that statement, trying to understand what really high stand systems tracks mean, or high stand deposits, has caused a lot of confusion. It was part of the original Exxon terminology, and they still use it. And I think more people, though, now are beginning to go back to the old days where we talked about progradation, which is the same thing. You're prograding seaward, or regression, where the shoreline is regressing in a seaward direction, rather than high stand deposits. Well, there's names for each one of these deposits, and so the sediments that are deposited out here during the falling stage, we call those low stand systems tracks. You know, again, we all different groups have their own languages, just like engineers have a different language than geologists, and half the battle is understanding each other's language, you know. And when you sit down in a room to try to figure out whatever you're looking at, one example of that is deep water. The word deep water. I used to sit in on meetings with engineers. We were exploring for deep water, and the engineers would be talking about deep water, and I'd talk about deep water, and pretty soon we realized we weren't talking about the same thing. And the engineers were talking deep water, what your water depth is from the sea surface to the sea floor, okay, where you drill down through the water and then into the sediment column. What I was talking about was how they formed originally with the fall in sea level. So another one is, another example is that I used the relative permeability. Yeah, I use the term relative permeability differently than you do. I'm talking about high versus low permeability. It's all relative, but you guys have your own, which is different. It's the relative permeability. So half the time when you form a group, you have to learn each other's technical language, and that's really can be an issue sometimes. All right, so at any rate, so I'm just going to repeat this again. During the falling stage of sea level, where we have the red line, this is what you get. In shallow water, you get erosion and formation of a sequence boundary. And in deep water, we have submarine fan. Those are the deposits during low stand time. Okay. Well, actually, let me take that back. I'm going to call it used to be called low stand time. Now the newer terminology is falling stage systems tract. In other words, sea level is falling, and the term low stand is just restricted to this little turnaround point down in here. This is a turnaround area.
What would the channel levy
In fluvial or deep water?
in deep water?
Where would they occur? They would occur somewhere down along here, because what happens is that in deep water, as you're eroding up here and depositing down there, the coarsest material will stay in your deep water channel and form a fan out at the end of the channel, but the finer grained material in the flow, because these flows are turbulent, the finer fraction spills out over the top and forms levees alongside. So the levees and the fans are just about same time interval. Same time interval.
But they could occur either in the surface or in the bottom. Am I correct?
Surface. On land.
On land. Yeah.
Oh, yeah, well, we just have different names, yeah. We call them, usually in deep water, we call them levees. And in the fluvial environment, well, we call them levees and splays. Yeah. The difference is that on the ground surface in a non-marine environment, the levees are associated with what we call the meandering river deposits, okay? Whereas in deep water, where you've got the submarine fans, the levees are more associated with the submarine fan. So that would be a different, yeah.
Excuse me, the slumps are when the sea level are increasing or decreasing?
Is what?
The slumps.
Levees?
No, the slumps.
Slumps, oh.
They are when
Yeah, see, they're way up here.
when the sea level is decreasing.
Just starting to drop, you create a difference in pore pressure, and so the upper slope becomes unstable and it moves down. Now the same thing can happen on the rise, where you're changing the pore pressure also, but usually the big slump deposits are the ones that occur during the early falls. Yeah. Slumps or debris flows is what I call them here, but yeah, slumps and slides and yeah. Okay, so that's what you get during the falling stage systems tract. Now, during early turnaround, which is now what we call low stand systems tract, that's when you start to backfill your incised valleys, kind of coming around the bend here. Okay? Now, when your rate of rise increases, when the rate of rise increases, that's when you get your big shales, because you're increasing the water depth very quickly, relatively quickly. So you get your very fine-grained shales and organic matter deposited then. I talked yesterday about what we call maximum flooding surface. That would be the top of the condensed section or the top of the shaly zone, and it occurs right there. So that's the maximum flooding surface, which is a surface and the condensed section forms just below that surface. The maximum flooding surface is the top surface of a condensed section. Condensed section is the organic rich shale. That's what forms your unconventional resource shales, for example. They occur this part of a sea level curve. Okay, so I like to, by the way, you probably figured this out by now, but when I lecture, I like to kind of show the same thing several different ways, several different pictures of things, because somebody might understand one picture but not another. And so I figure if I show a variety of pictures showing the same thing, then it'll lead to better understanding. So it's a little bit boring that way because I repeat a lot of things, but using different figures. So deep water now refers to sediments deposited out in the deep environment. This picture, they're called basin floor fans, submarine fans that are formed on the basin floor. And the sediment that supplies those come down rivers. And at this time, your shoreline let's see, I'm going to do this backwards. Okay. Well, let me do this backwards here. Okay. Let's do a transgression first. During well, I can't do it that way. Okay. During a fallen, this would represent a fallen sea level. Okay. You get this configuration. The shelf edge is here. All this is severely exposed, so you get your incised valleys and the like. And then that sediment that's carved out to form the valleys is deposited out on the basin floor. Now let's transgress so that our shoreline now is moved landward. So now all of this that was severely exposed before is now underwater, in shelf waters, and here the blue line is the shoreline. So you're gonna no longer, well, one of the things that's gonna happen is no longer are you going to get sand deposited out in deep water, okay? Because you've got a certain amount of water here in this area right here. So no longer do you get sand deposited in deep water. Where's the sand going to be deposited? Well, it's got to, if there's any sand in the system, it's got to be deposited somewhere. And so it gets deposited along the shoreline. And just think of successive stages of rising sea level, where you might have the shoreline here, you get some sand bodies, then sea level rises, you get a shoreline there, some more sand bodies, shoreline there, and so on. Now we go back and we do another drop in sea level. So this is our low stand shoreline. What I'll show this afternoon is a very interesting example of a study that was done, a sequence stratigraphic study done in Pennsylvanian age rocks, where you could work out the positions of incised valleys because you knew these were Cretaceous age rocks. You knew where the transgressive shoreline was, and you knew where the low stand shoreline was. And so looking at that area in between on seismic and on well logs, one could actually work out where the incised valleys were in that area between the low stand shoreline and the transgressive shoreline. Now where would the high stand shoreline be? It would probably be somewhere along here. And let me clean this up. high stand shoreline now might be a little bit seaward. And you'd have a delta forming right in there. Okay, so that delta pushes the shoreline seaward. Now, I showed an example yesterday. This is a very good diagram to go back on that example, because someone had asked me about this. Is there anywhere where you can get transgression and regression at the same time? And I said the answer was yes, and I used an example of the Mississippi River Delta. And so I'll kind of draw that while I've got that out here, where during high stand time, you've got the Mississippi River forming a delta there near the mouth of the river. So you're prograding here, and the shoreline is going to move seaward over here. But you're not receiving any sediment in this area or in that area. So what's going to happen there is just you're going to have normal subsidence because the weight of water will work on the seafloor to cause subsidence. When you have subsidence, sea level essentially rises. Okay, so you have, at one instant in time, you have progradation in one area, near where you have a major river forming a delta that's prograding. And out here, you've got no sediment, but you do have subsidence, so sea level is rising, like that. So you can get different types of sand bodies. So here, for example, you'll get your delta sand bodies. Back up in here, during transgression, you're going to get these shoreline sands deposited there and deposited there. So two different reservoir types that you have in that one interval. So this is one of the complexities of sequence stratigraphy, because if you, and I think I mentioned this yesterday, whoops, I shouldn't have done that, but let me redraw that. So you get a delta here during, so progradation, transgression there. So you get transgressive shoreline sands right there. Or we can put them right here too, for that matter. So one of the problems that this caused before we had 3D seismic, when we only had 2D seismic, one of the problems that caused was if you looked at a 2D seismic line that went across like that, you would interpret this as a delta and say, well, this must be a high stand time. This time interval you had that this delta was formed, it was high stand time. And then you look at another seismic line out here and you say, oh my God, you know, what's going on now? Now I've got transgressive time. But in reality, it's the same time, but in different positions, you're getting different processes happening. And that was a real issue during, in the days when we had 2D seismic, because you might, for example, take this seismic line again and run it and say, well, we've got a big delta here, so let's drill our wells out here, out there, something like that, and you might drill you drill a well and there's no delta, okay? Now 3D seismic has kind of eliminated that problem when you look at the horizon slices. So, erosion during subaerial exposure in this area. All right, well, for many, many years, people who do seismic stratigraphy have used a single curve to describe what I've been describing to you. Well, a couple of years ago, I added kind of a complexity to that when I wrote my book. And what I said is that that's not entirely true. This is a great curve to use if you've got deep water deposits that you're looking for, because those submarine fans are going to occur down on the basin floor on this part of the curve. But supposing, but that assumes that you always get the same amount of fall and rise in sea level, which of course is not true. You'll get different degrees or levels of falling and rising sea level. And if you only have a small change in sea level, a small drop in sea level, we'll say, you're not going to get a submarine fan out in deep water. Why not? Because with a small drop in sea level, your shoreline might not get out to here, so the river brings in sediment, and the sediment's deposited here rather than out here. So you really need a big drop in sea level to move that shoreline all the way across, and so that the incised valleys can sediment can be transported in the incised valleys and out into the marine environment. If you just have a small drop in sea level, say here's the shoreline, and then there's the shoreline, that sand is going to be trapped in the shoreline. It's never going to get out into deep water. Okay? So what I did is I said, well, I'll do two curves, one for deep water and one for non-marine and shallow marine. So, and that's what's shown in green here, where what we have been talking about all this week is really what goes on there. We haven't talked about deep water sediments that would be forming down there. We're kind of confining ourselves to shallow marine and even non-marine waters. Okay, so you have a different curve. Sea level hasn't dropped as much. Remember, your vertical axis is sea level, so you get different types of deposits. And I'll show you what these are. I won't give you the names right now, but I will show them to you. So you have to take that into account as well. And like you guys, if you're working with fluvial and maybe shallow marine deposits, you're going to get a different set of features than if you were working in deep water where you had a major drop in sea level, or major change in sea level. So how much sea level change there is also important. Know how much change you have in sea level. So this is the Slatt curve that I published in my book in 2013. Nobody's criticized it yet, so either they don't care and they don't read it, or they agree with it. So once again, I'm being redundant here and saying the same thing in different ways, but again, I like to do that. Makes things a little boring, but I think leads to better understanding. So looking at the same thing in another way, let's say now we're looking at a cross section here. Let's say transgression. Okay, so here is our sea level at one instant in geological time. And then we have transgression, meaning the shoreline or sea level is rising. Okay, so sea level rises to this point in time. What are you creating in between those two instants in time? You're creating a sediment wedge. Okay, you're raising sea level from here to there during a transgressive period. And so you're going to have sediment deposited. What type of sediment are you likely to get? And that's that red wedge of mine. What is that likely to be? Well, it's likely to be a condensed section. Okay. You're raising the sea level, shoreline's moving landward, you create the condensed section. Let's take the opposite example. Well, here you get this surface that I mentioned before, transgressive surface of erosion would be this surface right here. And how it's forming is that as sea level is rising, that surf zone is moving across there and it's doing some additional erosion. So you get that TSR, TSE, transgressive surface of erosion. Now let's do the opposite. And we start out here as our shoreline, and we drop sea level. So now your arrows are coming down as we're dropping sea level. So we go from, excuse me, I made a mistake. No, this would be your initial sea level. And now we're dropping sea level. I want to make sure I do this right. Yeah. So we drop sea level to that point. So what do we create in here now? During regression, we're creating all of that area in there is going to be subject to erosion. Okay, because it's severely exposed. So we get another type of deposit, which we call a regressive surface of erosion, or RSE as it says there. And, well, I'll just leave it at that. So this is an example then that I said earlier where you might have a sequence boundary that formed during a falling stage of sea level, and then early rise, that surf zone comes across the shelf and creates a surface of erosion. That's a transgressive surface of erosion. But now, if you go to another cycle and you start to drop sea level, the same process goes on, and the first thing that might form would be a regressive surface of erosion, because your shoreline is moving back now, and that surf zone is moving back. So you end up with a very complex surface representing a long geological time period, where you had one drop in sea level, a rise in sea level, and another drop in sea level, the way I just described it. All right, well, a little bit of history here never hurts. And so actually it was in 1977 when that book was published. It was published by AAPG, the American Association of Petroleum Geologists, and they called it Memoir 26, Seismic Stratigraphy. And it provided the origin and foundation of the concepts of sequence stratigraphy that I'm going through with you here. It was done by those Exxon guys, and the fundamental concept, like I said yesterday, was the idea that changes in sea level, these fall-rise cycles, occurred repeatedly throughout geological history, and in different parts of the world, you would get the same effect, either a fall or a rise in sea level. You could go to the ocean here in the coast of Bolivia, and if you were getting a sea level fall here, you'd have a sea level fall in Asia, okay, on the coastline, minus the tectonics. tectonics might be different and more, change things more locally. So because of that, if you could develop a curve, like I've been showing you, and actually put age dates on those by biostratigraphy, by the fossils, we could then have a correlation tool for interpreting both at the fine scale reservoir scale or at the larger regional scale, exploration scale. The basic claim from Peter Vail and his group, he was the head of the group there at Exxon, was that from doing global studies, sequence boundaries are synchronous and at a global scale. In other words, they occur at the same time in different parts of the world. They had a term for this, and they called that eustatic sea level, eustatic change in sea level, meaning changes due to changes in the, we'll say in the volume of ocean water, so that sometimes you get a rise when you've got a large volume of ocean water, and sometimes you get a fall. So, and these would be global in nature. Well, that created controversy. Geologists are always controversial. There's always something to argue about. Okay, geologists are good arguers, especially over beer, and that's when we do our best arguing. So there was a controversial aspect to this, and there were all kinds of publications and meetings all about this theory of global eustacy, that sea level changed the same any parts of the world. And the controversy was from people who were structural geologists and tectonics people, who said that, well, that's not right, because you've got the tectonics here, and there, if you've got a sea level here and your mountain builds up, your shoreline is going to move. Okay, so it's local. So these are not global changes; they're local changes due to tectonism. Well, those people that argued that point have mainly been working in tectonically active areas, and so that would be true in their case. Whereas people that worked in more tectonically quiet areas, like, which is what the Exxon people mainly did, they would say, no, you know, everywhere we go in the world, at a certain time interval, we see a drop in sea level. And at another time interval, we see a rise in sea level. Therefore, it's global in nature. Okay? So that controversy went on for about 5 years. The sequence stratigraphers finally beat up the structural tectonic people and told them to quit whining and to face the facts. And so now sequence stratigraphy is, or both groups were correct. It depended on where you work, where you did your work. If you're in a tectonically active area, you're going to see a tectonic change in sea level due to tectonics, like I'll show you on the next slide. If you're working in an area like a passive continental margin, where you don't have any tectonism, then you're going to just see the changes that are due to global sea level changes. And so both were correct. It came to a happy medium. I don't know if it was happy, but they came to a medium. Just a very simple diagram to explain what I just said about tectonics. This is my one tectonic slide in this whole lecture. And so let's take it an instant in geological time. We have our shoreline here, our continental shelf, our slope, and a basin floor down there. And let's say here's our sea level right here at this particular point. So there's the shoreline, and the red line is the sea level. Okay, well, let's add some tectonism now to this. So we go from a passive margin to an active margin. And let's say this is what's going to happen, that we have uplift in the onshore mountainous areas and subsidence down here. The effect of that is that the position of your shoreline is going to be different. So where I have my little red arrow up here, up on top here, that's the amount of space you have between the sea surface and the sea floor. Down here, it's the same thing, except what has happened now. The shoreline was here, but now the shoreline is down here. So what is that? That's we call that a regression, or a progradation, in essence, or a regression would be a better word, but it's tectonically induced. Okay, shoreline didn't move in this case. It's the rocks that moved, mountain building, and so now you have your shoreline at a position like this rather than at a position like that. So that's how tectonic plays a role, and we use the term overprint to describe that. And a statement I feel safe in making is that you can, with a little knowledge of sequence stratigraphy, you can almost always find the eustatic effect by looking at well logs and seismic and the like. But sometimes in tectonically active areas, there will be a tectonic overprint. In other words, tectonics of somewhat lesser importance overprinted on that sequence stratigraphy or the eustatic change in sea level.
Dr. Slatt,
Yeah.
in this case, how much difference will be with that compared to the falling sea level? Because even though the sea level didn't change.
Well, it is. In essence, relatively speaking, sea level has fallen in terms of relative to the mountains.
Yeah. We
Okay.
have more land exposed, therefore
Right.
we're going to have erosion,
Exactly.
so it's going to be similar.
So it
to
behaves that way, yeah, just like if it was purely eustatic. Okay. Now, the way I explained it to you in this case is the sea level hasn't moved at all, and the land masses have moved. Okay, so, but it's the same effect.
Are we expecting to see a marine fan in this situation?
Well, that's a good question. Yeah, is the answer. And why is that? Because here, for example, in this lower one, where you have the tectonics, you've got more land mass exposed to erosion. Okay, so you're gonna have more erosion, and that sediment's gonna get out on the basin floor. Okay, you've also got less distance between the shoreline and the shelf edge here than you do in this case. This case, it would be hard to get sand from the shoreline all the way across here to be dumped out in the basin. Probably wouldn't get much sand, but here you would, because you're closer, the shoreline is closer to the shelf edge, and you've got a larger mass of rock to be eroded. Okay, so same concept, but different processes. That's why I only have one slide on tectonics. So that's everything about tectonics. And of course, I'm talking about pretty big scale here now, okay? I'm not talking about reservoir scale. I'm talking big scale, basinal scale features. Well, okay, so like I said, the sequence stratigraphers, people who do sequence stratigraphy have their own language, and just like all different groups, and it's no different with sequence stratigraphy. So remember, I gave you a definition when I started this of lithostratigraphy, and that is the correlation of rocks based on, I should say, description and correlation of rocks based on their physical properties or physiochemical properties. So what we call names that we apply are formation names. I'm sure you're all familiar with that idea of what a formation is. And you can subdivide formations into members. So here, for example, is a formation A. That's this one down here. A formation B made up of a shale. This is a well log, by the way. Formation B is made up of a shale interval. That's member B2, and a sandier interval is member B1. And formation C is made up of a nice blocky sand. Okay, well, that would be a lithostratigraphic description. Now, a sequence stratigraphic description is somewhat different. The rocks are the same, but the naming, the terminology, the nomenclature is different. So here we have the same well log again, okay? And now, let's see, I'm going to do, remember what I said, let's see, I'm going to have to modify this a little. Remember what I said yesterday is that if I were going to correlate, what would I correlate on? What surface would I want to correlate from well to well? And I said, well, the easiest one to see, which is going to be a high gamma ray kick, and that's going to be your condensed section. So, with the maximum flooding surface. So the first thing I do is I look for the high gamma ray kick, and the highest one is right there. That's your maximum flooding surface with your condensed section below it. So what are you going to expect beneath that flooding surface? A condensed section, which is really the condensed section is the upper part of a transgressive systems tract. I hate to bog you down with terminology, but kind of important in this case. What are you going to find above that maximum flooding surface? Well, you're going to get your high stand deposits here, okay? And they're going to be deltaic in character. They'll have a nice progradational shape to them. So that's what you see there. Then you see a sharp break and a change to a blocky rock. And I would interpret that as an unconformity or a sequence boundary, where I get that sharp change. And then sitting on that sequence boundary would be your low stand systems tract. Now down here, a little bit different, because you've got your high stand systems tract here, and then I've got the unconformity, the sequence boundary, but what's missing here is the low stand systems tract. And the reason for that is because I'm in shallow water, and shallow water, I'm not going to get any submarine fans deposited at that time. So at that instant in time, no submarine fans. What I get is a surface of non-deposition. So I still have a sequence boundary or an unconformity, but no low stand systems tract because I'm up on a shelf. Now, If I had a well log down in the deep water, it would look something like this. And here you get a nice big blocky sand. I'm not a very good drawer, am I? Shaky hands, I guess. But this is supposed to be a blocky sand at any rate. And that would be your low stand systems tract if this well log was out in deep water. Okay? So what are you going to correlate with again? I'm going to correlate with this high gamma ray. So in terms of geological time, this instant in time right here, where you get your highest gamma ray, correlates to this instant in time. Okay, so, whoop. Slide go. Okay, so I've got now two unconformities or sequence boundaries. So the material in between defines a sequence. Remember I said a depositional sequence is bounded at the top and bottom by unconformities. So notice the difference in terminology now between this and lithostratigraphy. Now here in this picture they call this chronostratigraphy, and chrono is the Latin word for time. So once again we're basing this on time stratigraphic surfaces, not the formations, as our primary subdivision. Then we can add the terms low stand systems tract, high stand, and so on. Okay, so who cares? Who cares what you call it? You know, I mean, that's the ultimate question is why are you sitting listening to all this stuff I'm talking about? Does it really matter? Well, the answer is yes, it matters a whole lot. And that's illustrated in this diagram. This is another one that I use as a screensaver because it's so, I always want to remind myself of how important these things are. So here we have a well here and another well there, okay? Both wells have a sand body. See a nice, let's say these are gamma logs or SG logs, and you have a nice sand body there and there. You don't know what's in between those two wells. I've drawn it for you. That's my interpretation. I don't know that. The only hard data I have is what is at the wells. And I know that I've got a sand at the top of both wells. So the common tendency is for you to correlate those two sands and say they're the same sand. Okay, same sand. However, there's another possibility, and this would be your sequence stratigraphic or your chronostratigraphic possibility, where you had deposition, you had progradation of and development of a sand body, a little shale break called T1 here, then another sand body, another progradation called T2, another sand body, progradation T3, and then the most modern sand body. And this is a succession of basically prograding deposits, but you've got these little shale breaks in there. What are those shale breaks? Well, those are where you have very periods of transgression. So, progradation, so let me go back over this and add to it now. You have progradation, and you then have Little shale is transgressive. Progradation, transgressive. Progradation, and transgression. Okay. Well, so who cares still? Why does this really matter? You do one correlation or the other. Well, the significance of this is that here you're saying that you've got a continuous sand body from one well to the next. So like if you're gonna water flood, you say, this is a simple water flood. I'll just inject water here, and the water comes out here, and I get more oil produced over there. But in this case, if this is true, then the water may never get past. You may inject here, but the water may never get past that T1 shale, that transgressive marine shale. Okay, so the water's gonna get in there and it's gonna go sideways rather than the way you want it to go, long ways. Well, how can you tell the difference? Is there a way that you can tell if you've got this situation or if you've got that situation? And there is a way, and the best way to do this is, once again, using your biostratigraphy. Remember, I keep saying biostratigraphy is the backbone of stratigraphy. Well, what do I mean when I say that? Well, what I could do with these wells is I could take cuttings, and I could take cuttings, say, I don't want to take cuttings in the sand body, I'll take cuttings in the shale. So I'll take some cuttings right there, just below the sand body, and I'll take them right there. If the ages, if they have the fossils, and I can determine the ages, and if the age is the same at both, then I have a high degree of confidence that I can correlate this way. But if they're not the same, then I have a higher degree of confidence that this is the case. And what would happen? You'd find fossils here that were older than fossils here. Okay? So this was deposited first. So you get the older fossils. Deposited there, you get younger fossils. So now you know that you've got a pattern like that, and that your water flood is not going to be so simple. That you may have those shales acting as barriers to movement of that water. So this is why it's important to try to figure out what you've got. And I prefer to, when I have the data, I prefer to do the sequence stratigraphy, or as it's called here, the chronostratigraphy. Because then, if I'm designing a water flood or something like that, then I can figure it out. So the first case, continuous reservoir. Second case, discontinuous reservoir. Okay, big difference. One more example of the different differences you get in correlation. Here's a set of 4 logs. And you see a sand body here, a sand body there, one there, one there. Little thin sand here, barely can see, thin one there, then one there. and then you've got another sand in these two wells. So you make this correlation. This is the correlation you make. I got a single sand body here that's continuous all the way across. And this one's continuous all the way across. And this one is continuous across well B and C, but not, it doesn't extend to well D. So I could make that sort of an interpretation. And that would be a lithostratigraphic interpretation. I would make that interpretation on the basis of looking at the rock properties. As a yellow sandstone, what are its properties? And so on. Well, there's another interpretation that one can make for the same sequence of rocks. And here it is there. If you use your biostratigraphy, what you would find is, in this case, to get this case, you would find older fossils, little younger fossils, little younger, and a little bit younger in the shales associated with each of those sand bodies. So this, if that were the case, if you knew that these were different ages, see, in this case down below here, you assume a single age for deposition, okay? And you could go to your shales below there and take some samples, and if you get the same ages from the biostratigraphy for each of those wells, then you can say, okay, it's probably continuous, I'm okay, my analysis. But if you get something like this, where this is older, younger, still younger, still younger, this is the interpretation that's favored. And we looked at an example of this yesterday, I think it was, where we had a sand body here, another sand body there, and these sand bodies are kind of climbing stratigraphically as you go from right to left. Well, again, what's the difference? Does it really matter? Well, of course it matters in this case, because your sand body shown in yellow is either going to be continuous or discontinuous. It can be either one sand body, or in this case, 4 different sand bodies. In this case, separated by the shale, which is shown in blue in this diagram. See, I get so carried away with this, I forgot to take another break. So why don't we go for about 5-10 minutes, and we'll just break for lunch. All right, so let's assume now so how are these going to form? Let's see, how, if we assume this is the correct way, how is that sequence going to form? Well, this represents a period of progradation, fall in sea level, progradation, marine transgression, rise in sea level. See my little arrows that are going the different ways? So progradation going seaward, transgression going landward, give you a shale deposit, progradation, give you the sand, transgression to give you the shale, sand, progradating sand, shale, transgressing shale, progradating sand. So that would be the explanation that way, to account for that sort of correlation. And again, you know, if you were using this correlation here, you might drill one well. Say you drill a well like this, and where would that well be? Let's see. In this case, would be equivalent to doing that. But you work with the drilling engineer and you tell the drilling engineer, I want to go down to a certain depth and then just go straight out, okay? In your landing zone, where really you want to do a slant well. Okay, so you hit all of these sand bodies. So at any rate, all of this stuff is complicated, but once you get the hang of it, it really is quite simple. And we'll keep on with that for the afternoon. Let me ask you one more question though. When you look at this stratigraphic interval all together as one stratigraphic interval, is that stratigraphic interval transgressing or regressing? Land is to the left, sea is to the right. So is it transgressing or regressing? Taking the whole system together, all four. Transgressing, right. Because each one of those sand bodies is moving further and further landward. So if I were to draw a sea level curve, it wouldn't look like that. It would look like that. You see how I got that? Okay, so here's your overall transgression, the black arrow, and then superimposed on that are fall, rise, fall, rise, fall, and another rise. So this complicates things even a little further because now we've got different scales. Remember that the sea level curve is the vertical axis is time. So what that's telling us is that over a period of time, we're getting overall marine transgression, but within that time interval, we're also getting smaller periods of transgression, regression, transgression, regression. And this is really, if one wants to use sequence stratigraphy for reservoir characterization, this is really the scale you want to be working at, where you get the superimposing of one scale of sea level change that has superimposed on it a smaller time, a smaller or a less time series of fall rise cycles. So why don't we break for lunch and we'll pick up on this after lunch.